understanding really fundamentally much more about the periodic table. Sounds like a dumb thing to say, but like when you teach the periodic table, periodic trends, and all sorts of things over and over again, you actually start to pick up on some subtleties that are surprising, in the way that it works.
Warmly welcome for another segment of series of interviews organized by Department of Chemistry at University of Colombo. I am Vihanga Sankalpa Medibakar, fourth year undergraduate student of Department of Chemistry at University of Colombo. Intentions of these conversations are to develop a better vision of science and to arouse student interest about learning new things from lives of great personalities in science. Without further ado, let me introduce our interviewee of the day. Today's discussion is with Professor Justin Caram. Professor Caram is an assistant professor at University of California, Los Angeles. Welcome to our session, Professor Caram. We are honored to have you here. How have you been doing these days?
We are doing as best as we can. The current situation in the US is we've been under sort of COVID restrictions in California since March of last year. Currently, we're allowed to do research, but all of our teaching is being conducted online. And the research we do, we're still limited in our amount of students we can have in lab. So, we're doing the best we can. But, my students have been pretty solid and striving, and we're learning how to teach online. And in some ways, we've learned a ton. And so, and I think the world will be a little different place after this is done. So we'll see. But, I'm personally doing great. So.
Okay, Professor. First of all, could you please give us a brief introduction about yourself?
Sure. My name is Justin Caram. I am from a small town a medium-sized city in Pennsylvania called Allentown, Pennsylvania, which is near New York, pretty close to New York City. It's on the east coast of the United States. My parents are actually from Argentina, so they emigrated to the U.S. My father came actually to do his PhD studies at the University of Minnesota in chemical engineering. And he actually is a professor of chemical engineering at Lehigh University, which is a university in Bethlehem, Pennsylvania. It's a primarily engineering focused school. And so I grew up kind of in an academic world. My family all went to college, and it was really important. Education was very important to us. And then I did my undergraduate at Harvard University, where I majored in chemistry. And I actually did not start interested in chemistry at all. I was interested in economics and international development. And I took one economics class that I did very poorly. And I took chemistry classes just to keep my family happy. And admittedly, I did much better in those, and I kind of ended up liking it more. And so I switched briefly to psychology, then to biochemistry, and then to chemistry. And I would have probably drifted into physics if I didn't have to pick a major at some point. So in the US, you kind of have some chance to decide your major almost into your second year of undergraduate. After I finished, I did research at Harvard, and I worked in two labs. The first one I worked on was atmospheric chemistry group, where we were studying sort of the kinetics of iodine monoxide reactions. And it's a kind of an important ozone depletion. And then I switched over to colloidal physics lab, where we looked at scattering and tried to understand how basically how spheres and other objects sort of rotate in 3D space using some light scattering methods. Those were great projects. I made no scientific contribution whatsoever, other than I learned a ton and got to hang out with interesting people and got to talk to things. And then I went to my graduate work at University of Chicago, where I studied, I did ultrafast spectroscopy under the direction of a Professor Greg Engel. And there we worked on a lot of different interesting things, including sort of photosynthesis, how energy moves in plants. Really doing this, studying it on the time scale that this happens, which is like femtoseconds, 10 to the minus 15 seconds. So it was really fascinating to study. We got interested in these questions of quantum coherence, like to what extent does quantum mechanics play a role in enhancing energy transfer? And then towards the end, I built a lot of fancy methods that are very difficult to do, and we would conduct certain experiments. We're using ultrafast. We did something called two-dimensional electronic spectroscopy, which is a very fancy and complicated method, but it's really interesting, and it lets you access these very fast timescales. Towards the end of my PhD, I got interested in materials, specifically, quantum dots, for example. So quantum dots are little tiny bits of floating semiconductors. They're tiny, and they are fascinating because they are really amazing chromophores. They absorb and emit light very efficiently, and you can tune them, and they have some behavior that is somewhere between molecules and semiconductors. And that got me kind of excited in the world of materials. So sorry, I'm giving you my whole life story, but like I went on to do a postdoc at MIT, mostly under the direction of Professor Munji Bawendi. So Munji, he's a pioneer in the field of quantum dots. He's basically invented the main synthesis, the hot injection synthesis of quantum dots, and then in addition has done beautiful work on the spectroscopy of single quantum dots. And while there, I kind of got really sucked into the idea of doing sort of single molecule microscopy and spectroscopy, and trying to use sort of interesting methods that kind of build on my background in ultrafast spectroscopy, but apply it to these sort of single quantum dots or materials on the sort of small scale. And while there, I got interested also in analogs to photosynthetic antenna, so things that are like molecules that assemble into complex structures that guide and that they can absorb light and then move it around. So these are molecular aggregates, for example. And so after a few years at MIT, I got a chance I went on the faculty market, applied a couple years in a row, and got a faculty position at UCLA, University of California, Los Angeles. So this is a big state university, one of the main state universities in California. It has, we have, I don't know, 35,000 undergraduates. So it's a very large school, and we have a big PhD program. So I'm about 3.5 years into or 3.25 years into my independent research career, and I have 7 graduate students and a postdoc. And so we're slowly publishing our first few papers, and yeah, it's been really interesting, developing some new microscopic methods and building new materials. That's kind of our big direction for absorbing and interacting with light.
Yes, sir. We all had an ambition in our childhood. What was yours?
Yeah, it was not science related, to be totally honest with you. I love history. I've always loved history, and I still do. And I think I wanted to, I liked reading, and I wanted to I think I was planning probably to go into the humanities or liberal arts, and then, not that it changed for any practical reason. I just realized that I think I like research in the sciences, and I like the intellectual aspect of being in the sciences, but and I prefer to read about history rather than do history research, which is very hard and involves a lot of very hard work. And it's more fun to read the masters who do that instead. So, I definitely was not expecting to go on this path. But I think once I started researching in lab and realized that it's something that I like, I don't mind sort of uncertainty, I grew to love this particular way of living and things like that. And I like the challenge of it.
That's very interesting, sir. Okay, let me ask it like this. What is the turning point of your career? What factor motivated you to learn chemistry?
Yeah, so okay, so we'll start with the sort of boring answer, which is that when I started my undergraduate, and I was thinking I might major in economics, or actually I was really interested in international politics. Like I wanted to understand the world, I wanted to understand why countries develop differently. Um, and I had an undergraduate advisor, and I said, my parents, they want me to keep my options open. And they said, like, and basically, since chemistry is the central, it's a cliche to say it's the central science, but basically, to go in any correct direction you would want to go, whether it's towards engineering or whether it was toward biology or go to medical school, you had to take chemistry, and you should take it in your freshman year, your first year of college. And so, my advisor gave me the best advice I ever gotten, which was, you're here for 4 years, it doesn't hurt you to do one thing to make your parents happy. I know that sounds a little funny, but if you're going to do one thing and take one class and make your parents happy, just do that. And if you don't like it, you just don't have to do it anymore. And so I took freshman chemistry, and I'll admit that it wasn't that I liked it. I kind of I liked that it gave me a lot of intuition for the world. That I felt like I left that class and I felt like I could understand why why my hand didn't go through this table when I put my hand there. Just little basic things of like how chemicals and bonds formed. And to be honest, I think though the most powerful experience for me was organic chemistry, because in organic chemistry, it's like all of a sudden the world opens up for you, and it's so elegant and beautiful in the systematized way of thinking. And even though I'm a physical chemist and I could not take an NMR to save my life, I can tell you that I still think organic chemistry is the way that I can't imagine getting excited of chemistry without having the experience of having a really excellent organic chemistry class. So that's kind of, I think, the turning point when I said, okay, I'm really happy and excited to do this one thing.
That's interesting. Professor, according to my experience, when I stuck with the problem in chemistry, I think it in microscopic level to solve it. That's how I feel the problem. According to your experience, when you are going to solve a problem in chemistry, what kind of thinking patterns you mostly use? How do you
Oh,
feel it? Do you feel the problem, and how do you achieve the answer of it?
okay, that's a great question. So actually, I've been thinking a lot about this lately because, and I would say this is not something that I would have come up with even a year ago, but I've been working a lot more with physicists lately because we're working on questions related to quantum computing and special materials and quantum, interest in quantum states and developing new methods to do this kind of thing. And what is interesting is that I realized that there is a fundamental difference. It's not that chemistry is like physics but simplified or something like that. There's actually a very fundamental difference, which is that you have, as a chemist, I like to think of it as you have a few superpowers. The superpowers is that you have excellent instincts for like what may happen when these two things interact with each other, when two molecules interact with each other, when a bond forms. You have an excellent instinct as to what the properties might be. And you might be wrong, but I think that you don't look at anything. We have a lot of like rules of thumb. And I think that's the entire field of like, I'd say physical organic chemistry, for example, where it's like you have lots of rules of thumb that are based on pretty scientific grounds, and they let you really access stuff that's quite complex very quickly. Um, and I'm learning that like this helps you move very fast on problems, and you will be wrong sometimes and you won't get the details right, but very often you'll be able to like come up with real intuition. And so I actually, I mean, for most of the things I think about, I do try to come back from a chemical mindset. And like you said, I think compared to an engineer, for example, in engineering, everything is very macroscopic properties. Wood has this property, this plastic has this property. And in chemistry, it's really not about that. It's about what's the molecule that makes this up and why, and what are the pattern of bonds and intermolecular interactions that make this work. And I think that's a really powerful mindset to have.
Okay, Professor. As you mentioned before, after your high school, you attended Harvard University and had conducted research with Professor Jim Anderson and Vinnie Manoharan to study
Yeah.
trace atmospheric radicals and self-assembled colloidal nanoclusters. I would like to know what you found from this research. What is main targets?
Oh yeah, so many different things. So when I started, I was working in this atmospheric chemistry lab. So Jim Anderson is a extremely famous atmospheric chemist, and his main, I mean, his like super important contribution to the world, and is that he actually has this beautiful experiment he did where he developed instruments that measured um, CLO, which is a type of chlorine monoxide. It's basically a gas, a radical that is responsible for the ozone hole, right? The hole in the ozone layer in Antarctica. And he used to build these precision instruments that would fly, and they flew into the ozone hole, and he would measure CLO and ozone at the same time. And he has this famous graph where you see CLO go, you see the ozone go down, and the concentration of this radical simultaneously go up. And what's really amazing about this is that it is the graph that got them to stop using these chemicals called CFCs, which were primarily responsible for generating the ozone hole. And it's an amazing story, and it's a basic science story. I mean, he built instruments, fundamentally instruments, that can measure these things with such precision that you could put them on a plane and they would survive and be able to do this measurement. And these used to fly spy planes to do this, by the way, because they would do this in the troposphere, so they would have to go very, very high up. And so basically, these are like almost like space. People are wearing like masks. It's like flying in space, basically. And so that's really when you see people working on problems like that, you realize, there's like maybe you'll have your entire career and you'll have nothing that'll hit like that, but maybe you make one or two contributions that in that case I think really did change the world, because it was an experimental confirmation of the Molina and Rollins model of this particular thing. So I learned a lot about instrument building and like the challenges of building precision measurements. And then in Vinnie Manoharan's lab, I learned a lot about, he was a new professor, so he was setting things up. And the way he approached science was just out of pure curiosity. He drank 10 cups of coffee a day and would come in and say, okay, what's interesting? What are you thinking? And you could ask him weird questions like, well, why do viruses assemble the way that they do? Why do nanoparticles, adopt these sort of shapes according to this like very strange parameters of thermodynamics? And he did these beautiful experiments that were just very elegant, where you could use colloidal nanoparticles as a model system to explore solid liquids and gases and fundamental interactions of matter. And he also had this beautiful holography type measurements where you can measure three-dimensional positions of atoms. And, there was just a cool, interesting, and dynamic experience for me.
It's so important. Professor, I saw that you have specialized many type of areas in science, like analytical and biophysics, like materials, nanoscience, etc. Would you like to know more about? I would like to know about what is biophysics and what are the areas you have focused on?
Yeah, so I'll admit, so for biophysics, for me, there we have a pretty broad. Our research program is pretty broad, right? And I'll freely admit that we use a lot of terms, in part as a way to recruit students who are interested in these various areas. For example, for biophysics, I think our primary research questions are related back to these questions about photosynthetic energy transfer still. And so what we're interested there is if we can think about how plants guide energy efficiently to the reaction center, can we think about analogous supramolecular complexes which do so as well? And one of the tools we use is by, you can take a molecule and you can self-assemble it into sort of an extended chromophore structure. You can take a chromophore, like a dye, and they'll self-assemble it. And these molecules will talk to each other and they'll communicate with each other through coupling. And it turns out that that is exactly the same way that photosynthetic organisms actually do this type of energy transfer. And it has actually it's kind of a fun model system to explore fundamental theories about energy transfer and strong coupling between chromophores. But even more than that, it's it's also kind of moving into the next level, which is how do we engineer these types of interactions if we want to use them for any purpose. And so I have found that this falls type of research for in terms of biology falls under the general realm of what we call quantum biology, which is really a fun term to use. It causes all sorts of problems because a lot of people say that there's no such thing as quantum mechanics in biology, and they're right in the 99% of the cases. But it's in these edge cases where you have very fast dynamics that you really want to build up a ground up understanding of these things. And I have found that students are really excited to work in that area. I mean, it's a really fascinating set of problems. Where does the line stop between where's the line between the quantum world and the classical world, and is it relevant to the dynamics of living systems? And I hope that we can, in our own small way, address some of those questions.
Okay, Professor. After completing your PhD, you have studied photophysics of nanomaterials and supramolecular structures. Would you mind to give us a brief description about this study?
Yeah. Okay. So, like I said, I went to work in Professor Munjibawani's lab, and when I arrived, there were several different research projects going on. The first part was that there was a program, an opportunity to do research on infrared emissive materials. So this was at the time what was really this is essentially you can design quantum dots. So quantum dots are semiconductors, and there are different types of semiconductors that have different band gaps. And one of the most interesting versions of this are lead sulfide, lead selenide nanocrystals. So lead sulfide is a semiconductor, and it has a band gap that is deep in the infrared. For that reason, you can tune it by confining it into a quantum dot or making it into a smaller quantum dot. You can tune it all the way through the visible. And this was an exciting material for solar cell applications because you could actually tune it to actually have the optimal amount of absorption for the sun. And in addition, it had other nice parameters, like you could put it onto a surface and you could get very high photovoltaic efficiencies. It was very easy to process it over long ranges. And, there was a lot of interest at that time in maybe making new types of solar cells out of quantum dots directly. And so what we wanted to do was study what's the properties of the single quantum dot in those types of materials? Like what's the actual single lead sulfide nanocrystal properties? And so this was hard to do because you didn't have any, these are infrared emissive, and so you needed to develop new tools to actually study these individual single quantum dots in the infrared. And you also needed to, I had to build a microscope and kind of probe these systems, and also use special detectors that can detect infrared photons. Because normally you can only detect visible photons with these sort of high efficiency detectors that you need to do single quantum dot spectroscopy. So I did something that I don't recommend people do. I kind of embarked in two projects simultaneously. So I had that lead sulfide project. And then at the same time, I started working on a different project with supramolecular aggregates because there was a postdoc leaving who had developed some very interesting new aggregate systems where there's these strong coupling among these chromophores. And, I was just curious, how far do excitons or does energy move in those systems? And so there is no necessarily tying force between these two projects. Just my willingness to bang my head against the wall and publish papers on two different areas. But the nice thing was that they did complement my the skills I had built in my graduate work. One was more on the quantum dot side, which I built a lot of skills on understanding quantum dot photophysics, and the other side was the understanding photosynthetic energy transfer, which is the same thing as what was happening in these supermolecular complexes. In the end, what's very funny right now is that my research areas have reconverged. So in my current group, we try to make infrared photoactive supermolecular aggregates. So we use both things simultaneously. And so it wasn't a waste of time. I did learn a ton, but I don't know if I would recommend doing too many different projects at the same time. It was a tough 3 years, I'll tell you that much.
Okay, Professor. As you mentioned, and I have seen that you have investigated several kind of research projects. My question is, what is the most interesting and most useful research project that you have done? And could you please elaborate it?
Interesting or important, these are all very different things. So, okay. I think that most recently, there have been a few areas that we're really excited about these days. And one of the areas that we've been publishing on extensively in my group is basically building up better fundamental understanding of how supermolecular chromophore aggregates, what underlies the photophysics of supermolecular chromophore aggregates. And so one thing that's fascinating is that, you can take a chromophore like a cyanine dye. This is one of the most common dyes in the world, used everywhere from biological imaging to used in paints to used in, all sorts of different used to be used in color photography extensively, although that's not as much of an issue anymore. If you take those chromophores and you put them into water at even relatively medium concentrations, not even very high concentrations, they spontaneously assemble into these very interesting structures. And their physics changes. The color, the absorption color changes, the emission color changes. You can redshift them, you can blue shift them, you can have all sorts of bizarre and maybe unpredictable behavior. And this theory, there had been theory that had been worked out for linear versions of these aggregates, and there are many, many examples of those kinds. But there had been much less work, for some reason, on cyanine dyes, especially in the fact that they form two-dimensional structures. And when you have two-dimensional structure, you have all of a sudden very different underlying physics, right? So all of a sudden you're not just talking about coupling in one direction, you're talking about coupling in multiple directions along multiple axes. And the topology or the phase space that you're exploring is far richer. And so I think over the last few years, we've developed a pretty robust research program in probing and sort of classifying and better understanding these types of aggregates. And it's interesting because it's very fundamental. It's basically saying, let's go back and say, what are the rules that set how these things assemble? And what can you tell from the photophysics of those chromophores in general? And then from there, now we're using that to actually make totally new structures that have never been made before, and pushing that direction a lot, and pushing basically the connection between structure and function in these types of aggregates. So that's kind of been the most exciting direction, or one of the most exciting directions that's happening in my group. The other exciting direction is we're just really trying to better understand infrared emission. So I think really I've really turned towards really fundamental chemistry or fundamental chemical physics questions. So one of them is, how red can you make a chromophore? Like, how red will it absorb and emit, and what can you make something actually emit light in past 1,000 nanometers? So we know that things emit light in the visible, 400 to 700 nanometers. You have some examples of near-infrared chromophores, but what stops you from being at 1,200 or 1,300 nanometers? And I think we're starting to get to some answers of how to make things that actually do absorb and emit out there. And so these are kind of my dreams, is to really kind of do whatever I want with molecular absorbers and emitters. you asked me what my most important scientific contribution is. I will have to
Yes.
tell you
Yes.
it's something kind of funny. But in my postdoc, this is going to sound really silly, but I had developed a method. It's really simple, and I didn't even really develop it. I kind of adapted a method to stabilize these types of aggregates in a matrix of sugar matrix, basically, mixture of different types of sugars. And it lets you basically do all sorts of different measurements that you weren't able to do on these systems before. So you could put them into low temperatures, you can do nonlinear spectroscopy, you can do all sorts of things. And it also makes them very robust to oxidation. So they sort of can live on the surface of the table for months at a time, and they're totally fine, when they were previously very, very photoactive. And it's just one part of one paper, and it's a trick, and it's kind of fun to think about. And now I keep finding myself reading papers where they're using this trick to stabilize all sorts of things in water. And even though it's not the main result or the main thing, it might be the most important thing I've done thus far. So I don't know. I mean, we'll see how that goes, but I think it's an inadvertent scientific discovery, but I'm pretty proud of that one as well. And I think part of
That's
it is
very,
just being open and talking to people. Yeah,
that's
I
very
don't know.
interesting. Professor, what are your ongoing research projects, and what are your future ambitions and future research projects? Uh,
Yeah, so I already mentioned the infrared emission thing. So essentially, the way to frame this problem is that there are very few molecules that absorb and emit above 1,000 nanometers. I can essentially list them right now if you wanted me to. And that's because it's very hard to design chromophores with homolumo gaps in that window. And not just is it hard to do that, even if you make something that absorbs and emits out there, it may not emit very strongly. The quantum yields will be very low. And so we're trying to embark on like a multi-level way of looking at this problem. So first of all, what sets the limits? What sort of are fundamental rules that set the limits? And there are some things, rules of thumb. How do we estimate those limits? And then how do we circumvent them? Can we use molecular aggregation to redshift chromophores? Can we use cavities? Like build a cavity, do some cavity electrodynamics or something like that, where you can enhance radiative rates by adding plasmonic systems or something like that. So that's one really interesting area that we're really excited about, because it's both fundamental, but it ties into a lot of materials questions. The other area I'm really interested in is more in the method development side. It's about developing new ways to probe photons. So essentially, photons that are emitted from a material tell you about that material, right? They tell you about the energetic disorder. They tell you about the fluorescence quantum yield. They tell you about non-radiative. They tell you non-radiative rates. They tell you about traps. They tell you about all sorts of interesting features. And so, how can we time and sort photons that in a way to maximize the information content that you get out of the emitted photon stream? And so we can use this to apply. This is especially important for nanomaterials, where you have heterogeneity from quantum dot to quantum dot, or from molecular aggregate to molecular aggregate, and you want to actually probe that particular thing. A third thing that we're really interested in is more towards actually sort of other types of 2D materials. So I talked about two-dimensional molecular aggregates, but lately we've been also working on two-dimensional colloidal nanoplatelets. And so a nanoplatelet, so a quantum dot is a sphere that's confined in all three dimensions that you grow using a chemical method. A nanoplatelet is one that you inject, that you grow, instead of growing a sphere, you grow a sheet. And it turns out that those have really interesting, and they're very different than the quantum dots in a lot of important ways. And one way is that you grow the sheet, and it's actually atomically defined. So you only have 2, 3, 4 monolayers of semiconductor. You can control how much you have. And because of that, they have interesting kind of new physical properties. They're very bright emitters, but they also have a very strong exciton binding energies. There's all sorts of interesting stuff you can do there. And I guess to tie all of this together is that our dream is to take these types of materials and then push them into the infrared. So again, like, right now there are very few examples of these types of 2D materials that are emit above 1,000 nanometers. And if we could develop those, they could be useful for a whole range of applications, from sensing to photon emission to biological imaging, for example. So that kind of ties all of the themes together. Is we're using spectroscopy to probe these materials. We're developing ways to resolve the photon stream coming from the system, and we're really pushing all of these things into the infrared. It's a broad set of topics for sure.
That's very interesting. You have got many awards. I have seen you have got many awards. What is the most valuable award of your life and why?
Oh, great question. Actually, the one that I value the most is I won a physical sciences teaching award when I was a graduate student. And what makes that one special is that it was my students who nominated and put me up for it. I didn't actually even request it or ask for it. They actually did it on their own volition. And to this, I really cherish that one because, it's a special thing. It's only given to a couple TAs, teaching assistants. And, it was really very, very nice of them it was an incredibly nice thing for them to do for me. And then, the rest of them, it's all very nice. I can't complain. I really appreciate the very nice things that people have done for me over the years. I've had a lot of great support.
Also, I think you have you're having many great experience in teaching in chemistry. What is the most memorable teaching experience have you got?
Yeah, so that's a great question. What's most memorable teaching? So I've started teaching freshmen, and specifically first year undergraduates, and I teach them. Actually, I teach the class that's not for. It's for life scientists. It's not for chemists. It's the chemistry for life science sequence. So most of the students are going to go into biology, or they're pre-health in some way. They want to go to nursing school, medical school, dental school, things like that. And I teach them first semester general chemistry, which is, in our case, it's about bonding, it's about quantum, like in the sense of we teach them about particle in the box, we teach them about the hydrogen atom, we teach them about how these molecular orbital theory. And there are a bunch of times in there where I get to go on a little bit of a tangent. Maybe it's talking about like why oxygen is so important, and like what the triplet states of oxygen, and the fact that this is actually one of the reasons there's damage in cells and things like that. And there's a few moments there where you do get this feeling like, even though this is not their major, they're like, oh, there is a reason that I need to learn this, and that I've actually learned something that will be, I don't know, will show up eventually in their future career, hopefully. And I really value that. It's a hard teaching assignment because you get people all over the place. But I don't know. For me, it's the kind of challenge I really enjoy, and certainly it's valuable for me. I've certainly learned enough in that class that it's been useful for my own research. Just going through and realize and understanding better. Like, this is going to sound dumb, like just like a way that understanding really fundamentally much more about the periodic table. Sounds like a dumb thing to say, but like when you teach the periodic table, periodic trends, and all sorts of things over and over again, you actually start to pick up on some subtleties that are, surprising, and in the way that it works. So yeah, it's a really fun experience.
I think teaching is the best way for the understand the subject.
Yeah, I definitely agree with that. I've had bad experiences. I taught graduate quantum. Taught graduate quantum I did not do it. I was learning a lot of things while I was teaching it, so I learned a lot, but I don't think the students I taught learned that much. So, it was a learning experience for me.
Okay, Professor. According to your experience, why do students learn chemistry, and what are the benefits they get?
Why should students study chemistry?
Yes.
Yeah, I think I mean I think it's a so chemistry has a few advantages in that it does have direct uh, from a lot of practical perspectives. It has, you can go to medical school, like in the US, for example, you can study chemistry, you can go to medical school, you can go to pharmacy school, you can go into a lot of different careers. But there is actually jobs for chemists, people who do chemistry, whether it's analytical chemistry, testing services, things like that, environmental chemistry, or synthetic chemistry, or even physical chemistry, in the sense of going to work at places like where they need people to use lasers and to understand chemical etching and to do all sorts of different things. And so I think one major value that chemistry provides is it's not just is that there is a pretty clear career path that I think is extremely broad, and you build both soft skills, lab skills, like really going in there, and wet chemistry skills, like going in and understanding a lab bench, that and then with a lot of actual quantitative skills, which I think are critically important in the modern workplace. And I think it's not that a well-trained chemist can really go in to any career in science, or even and almost any graduate type program that they might want to go to, with the right kind of attitude and the right kind of the necessary prerequisites, or whatever. And certainly I can tell you that even in my department, there are people who would fit in perfectly fine in a biology program, in a physics program, in a medical school, and there's tons of options for them, but they like teaching in chemistry and being chemists. um and I'll tell you, even from my perspective, like I'm a physical chemist, but I publish in physics journals, I publish in chemistry journals. I have, there's a lot of opportunity for me to go out there and really make an impact in different fields without having to stress about the arbitrary lines that are between them.
Professor, what are the upcoming job opportunities about chemistry? What is the future of chemistry? How is the future of chemistry?
I think there's a lot out there. I will say, okay, so big picture, I have a few things that I'm thinking of. I think that in the future, uh, I think that we are going to that it's about automation. I know this is a little bit of cliche again, but I don't anticipate that we're going to have in 20 years we're going to have graduate students running 100 reactions, running 10 reactions at a time in the lab. I think we're going to have a graduate student programming a robot to run 100 different reaction conditions and 100 different reaction conditions simultaneously, and running simultaneous NMRs on all of those different reactions, and really
Professor,
trying to probe and what?
Professor, do you
So,
mean a biological robot?
no, I think like just like flow chemistry, or
Like a
like you could have all sorts of ways to do that. It could actually be a physical like robot moving, like mixing thoughts together. But I think actually we'll be clever at designing our systems to do really big automation at the same time. Certainly in my group, I keep coming back to the idea that it's like, how if I know a little bit about how to automate a process, can I make this easier on my students? Is there a way to make this, instead of having to synthesize, to do 100 different reaction conditions to optimize something, can I set up micro reactions that we can test and really scan through that parameter space much more efficiently? So that's the challenge. I mean, I don't know how to do that yet, but I think that's the future. I really do. Lots of smart people are working on it, though.
That's very interesting. Professor, would you like to share your interest with us? How would you spend your leisure time? What are your hobbies?
Um, I That's a great. Again, I like to read. So I read a lot. Not always good things. I sometimes read a lot of fantasy novels and science fiction, and silly things like that. I read all of Game of Thrones. I read all of this Wheel of Time. I read a lot of very nerdy things. On occasion will play a video game or two. Lately, I just beat a game called Resident Evil, which is a horror video game. My wife and I, we live in LA, and since we've been here, we've started going to see movies a lot. And so before the pandemic, we were going to see, basically a movie or two every week. We had a special pass that let us go multiple times. So we saw everything, good and bad. We saw a lot of movies. So we like watching like really bad action movies and historical movies and things like that. That's
What is your
kind of how it's
favorite?
been my.
What is your
What?
favorite movie so far? What is your favorite movie?
Oh, what's my favorite movie? That's a great question. Well, we just we rewatched a movie called Fargo, which is a classic Coen Brothers movie. They're from the early '90s, and it still might be one of my favorite movies of all time. In terms of action movies, I love like Schwarzenegger movies from back in the '80s, like Total Recall and Commando. So, nerdy movies.
What is your favorite novel?
My favorite novel. That's a great question. I really like. So there's a book called Haran and the Sea of Stories. It's a book by Salman Rushdie. It's a children's book, but it was kind of not really a children's book. It's a beautiful novel. That's one of my favorites, definitely.
Don't you like Harry Potter?
Oh, and Harry Potter, of course. I can't say that I don't like Harry Potter.
Did you read it?
Of course, I've read all of the Harry Potter when they came out. The last one came out when I was finishing up my undergraduate, so I was waiting in line for the book then.
It's very interesting. Okay, Professor. We have come to the end of our session. Thank you very much, Professor Justin, for your valuable time and this inspirational discussion. I am very happy to talk with you, and we have learned a lot of things from your life and from your experiences and from your researches. So good. I am very appreciated.
All right. Well, thank you so much. This was really fun.